Section 6.4 is the last of the three types of conic sections that we'll be studying. So we've done parabolas and ellipses and now the hyperbola. So the first objective is going to be analyze hyperbolas with center at the origin. So we first have everything kind of with the origin as our basis, and then we move things around. So the hyperbolas have one more step than parabolas and ellipses, which is find the asymptotes of a hyperbola. Then the third objective is going to be to analyze hyperbolas with the center at any arbitrary point h, comma, k. So notice we're consistent of using hk for the vertex of the parabola, for the center of the ellipse, and the center of the hyperbola. And then the last objective, as always, is to solve applied problems to see that these are really useful shapes to know. So a hyperbola is once again a geometric object, so it's described as a set of points. So in this case, it's the set of points where the difference of the distance from 2 points called the foci are constant. So the foci are labeled F1 and F2. The line containing the foci is called the transverse axis. So the transverse axis, remember we had a major axis with the ellipse where we saw vertex, focus, center, focus, vertex. Well, the focus points are always inside the curved shape. So for the hyperbola, it goes focus, vertex, center, vertex, focus. But they are still all lined up. The midpoint of the line segment joining the foci is the center of the hyperbola. And the line through the center, perpendicular to the major axis, has a name. So perpendicular to the major axis is called the conjugate axis. So it's a little different than the ellipse. The ellipse, we had the major axis and the minor axis, the smaller direction. And the hyperbola, we have the major axis, and or also called the transverse axis, and the conjugate axis. Okay, so the hyperbola always will have two separate parts called branches. You'll also hear them called arms. And they're symmetric. There's a lot of symmetry going on here. If you fold across the transverse axis, matches. If you fold across the conjugate axis, matches. And if you fold through the center, you'll also get matching. So you have three types of symmetry. So again, you'll see a lot of symmetry in the equation that reflects the symmetry in the shape. So the 2 points where the hyperbola intersects the transverse axis are called the vertices. So the vertex is a point on the hyperbola. So let me back up a little bit, and the vertex is a point on the ellipse. And the vertex is a point on the parabola, so these points have to make the equation true. Okay, so we're going to start first with hyperbolas with a center at the origin. And we're first going to analyze hyperbolas whose transverse axis coincides with the x-axis, as you can see below in figure 35. So in your text, they go through the development of the equation of the hyperbola from the distance formula. We're not going to take the time to do that, but I want you to notice that the distance from focus 1 to any random point on the hyperbola minus the distance from focus 2 to that same point on the hyperbola, difference, remember, equals 2a or negative 2a. That's always going to be the case. That's how the hyperbola was constructed. So notice that this hyperbola is symmetric with respect to the x-axis and the y-axis and the center. So its equation must also have all this kind of symmetry. So here's the equation of a hyperbola with the center at 0, 0 when the transverse axis is along the x-axis. So this is this type of hyperbola. So we get x squared over a squared. This looks a lot like the ellipse. And we have y squared over b squared. This looks a lot like the ellipse, but notice we have a minus sign, so that makes it a hyperbola and not an ellipse. The 1 is consistent with the ellipse and the hyperbola. Then we have that c squared equals a squared plus b squared. So the equation for the c squared has a plus in it, but the equation for the hyperbola has a minus in it. So notice that this hyperbola has no y-intercepts. There is no point on the y-axis that belongs to this hyperbola. Okay, so the next thing we need to be able to do to find the shape of the hyperbola is to find the asymptotes of the hyperbola. So a hyperbola has two oblique, they're called oblique asymptotes. They're slanted. And the slope of each oblique asymptote is b over a. So it's always the number that's under the y term, square root of that, divided by the number that's under the x term, square root of that. And if you think about how we construct the hyperbola, this will make sense because we look under the x coordinate and go a and minus a to make these two vertex points. Then we look under the y term, just like for the ellipse, and go b and negative b from the center in the y direction and construct a rectangular box with those 4 points as the centers of the side of the rectangle. Then once we've made the box, the asymptotes are the diagonals of the box. And if you look at the slope of the line, you go up b and over a. So of course the slope has to be b over a. Okay, so here's an exercise that says find the center, transverse axis, vertices, foci, and asymptotes, and then make the graph and verify using a graphing utility. So if you're not doing the verify using a graphing utility step, I'd like to invite you to do that. Use Desmos, or there's another tool called GeoGebra that I'll show you in class. So we need to have a 1 on the right-hand side always. So we're going to divide both sides by 4. And we're going to get x squared over 2 minus y squared over 4 equals 1. So this looks almost like an ellipse, except for the minus sign between the two terms. So in the x direction, we go plus or minus root 2, which is about 1.4. And in the y direction, we go plus or minus 2. So x and y. And then we make a rectangular box where those 4 points are the midpoints of the sides of the rectangular box. Well, then we can draw the asymptotes for this hyperbola. Let me try and make it a little straighter. And we know we went up 2, so the slope of the asymptote, that's got a positive slope to it. We went up 2 and over root 2. Well, you should simplify that to root 2. So we have a slope of root 2, so the equation of this asymptote is y equals root 2x. Well, the other asymptote is always going to have the opposite slope. So we're going to have y equals negative root 2x because you go from the center, you go down 2 over root 2. So you get a negative slope. So this is the equation of the other asymptote that has a negative slope. Always one will have a positive slope, one will have a negative slope. So we can see that the center is the origin, 0, 0. the transverse axis, we can see from the picture, oh, we haven't drawn it yet. We need to look at the fact that the x squared term is first, and that's how we know it opens in the x direction. So we draw the hyperbola, make sure it's approaching the asymptotes in all four areas. So the transverse axis is the x-axis here. When we let the center move, then you would say horizontal, or you'd give the equation of the line. Okay, so then we need to label the vertices. Well, the vertices are going to be these points that are on the box and on the hyperbola. So this point is not a vertex. It's just a point that helps you draw the hyperbola to know how slanted the asymptotes are. So the vertices are going to be root 2 comma 0 and negative root 2 comma 0. So those are our two vertices. Then the foci, we're going to have to do a little work before we can find them. So it's little c squared equals a squared plus b squared. So this is the sum of the denominators. So c squared is going to equal 2 plus 4, or 6. So c equals plus or minus root 6. So then we know how far to go to get to the focus point. And root 6 is a little more than 2. So we know it's somewhere out here. Here is a focus point. A little more than 2, a focus point. So we can tell that the focus points have coordinates negative root 6 comma 0 and root 6 comma 0. So those are two focus points. And then we already have the equations of the two asymptotes. Okay, and then we'll do these puzzle problems in class together. And the second type of hyperbola that we're going to look at is the type where it's got the transverse axis along the y-axis, so it will look like it's been rotated 90 degrees compared to the ones we've been looking at. So here's where the center's at 0, 0. The focus is at 0, C and 0, negative C. Vertices at 0, A and 0, negative A. And then the B, all the B does is tell us how open the hyperbola is, whether it's narrow or wide, because the B is what creates the asymptote slope. So this type of hyperbola has no x-intercepts. So when the y term comes first, there are no x-intercepts. So let's go back and look at the previous one. And when the x term comes first, then there's no y-intercepts. So whatever way you come up with for remembering that for yourself. Okay, so here's the equation, and we have the equations of the asymptotes. And again, all the A and B do is help us draw the box. They don't tell us which way the hyperbola opens. So for the rest of this section, analyze the equation means find the center, transverse axis, vertices, foci, and asymptotes of the hyperbola, and then graph it. Okay, so I'm going to make another movie with the exercises so that we have time to do them carefully.